Good morning, welcome back. So, in the last class we were discussing about the uniqueness, maximum principles, and we have seen various cases. We also introduced the concept of regularity and uniqueness, as I said, you have already obtained, and what we have introduced is that we have seen that if u, though not complete proof, you have seen that if u is harmonic, then u is C infinity, and we also remarked that u is has much more regularity. In fact, u is analytic. So, let me see that what it all depends on the estimates on the derivative. So, estimates, that is what we are going to prove it, okay. Estimates. Let me make a remark there. Proving estimates before getting solutions is a part of PDE analysis. What we call it a priori estimates. A priori, that is very important in the study of PDEs. What do you do is that, assuming that there is a solution, you try to estimate its various derivative. So, estimates on the derivative. Okay. So, before that, as I said, I want to give you a definition first, which all of you know, that real analytic. Okay. U is said to be real analytic, said to be real analytic at a point x naught in omega if u has a convergent power series expansion. U has a convergent power series expansion in a neighborhood of x naught. That is, u of x can be expanded as thing, and this expansion is valid, okay, x minus x naught power n is valid for mod x minus x naught less than or equal to some number. So, you can derive that. So, I just given in the one variable case, but other variable also you can do that, analyticity definition, and this series n equal to 0 to infinity. So, in fact, I have some in fact, you can compute that. In fact, okay, I am writing it in one dimension. For higher dimensions you can study immediately. A n equal to u power n, the nth derivative at x naught by n factorial. Okay. So, you can actually compute. So, all the existence of so you have to be very careful. Existence of n derivative is enough to form the summation. That does not mean that the summation will represent the function back. You will be able to compute. So, okay, f is C infinity, f is so you let me make a thing, f is analytic at x naught implies immediately f is C infinity is differentiable infinitely many times at x naught. Okay. And if it is analytic at all points in a region, then it is called analytic in omega. Okay. If it is analytic at all x in omega, we say f is analytic in omega. Okay. But the interest is that f is C infinity does not imply f is analytic. That is what I say. You can have C infinity. I will give you a very standard example. If you have not seen this example, this is a very standard example. I am sure you would have seen it in the first basic course on analysis or complex analysis. So, you define h of x is equal to 0 if x is in less than or equal to 0, e power minus 1 over x square if x greater than or equal to 2. Prove that. So, this is prove that h is C infinity. Of course, it is C infinity except that the origin is obvious because 0 and e power. It is also the C infinity at the origin, and h prime of h any nth derivative at the origin is 0. Okay. That means the summation is always 0, right. So, but h is not analytic, h cannot, because h is non 0. So, this gives you, so if you form the summation based on h n of 0, you get the series becomes 0, okay, all the derivative, but then h is non 0. So, let me not do it, but h is not analytic. Okay. So, that is an example. So, that is an important result, you have it. So, to get estimates, the message is that to get analyticity from C infinity, to get analyticity, this is what the important message you have to follow. From C infinity, we need to derive estimates on all the derivatives. That is what we are going to, on all the derivatives. So, that is the message, and that is what the title of this section. Okay. So, we are going to derive some estimates. So, we are going to state the estimates first. So, and then as I said, I am not going to prove it, but I will give almost everything so that you can prove it, because you have to do something to do this one. Okay. So, the estimate, which let me prove it, is enough to prove it for one variable estimate. For any multi-index alpha, so okay, so it is all for harmonic function. So, probably you do not forget about that one. So, maybe let me state there. So, we take it as okay. Let so this is there our background. Okay. Let u be harmonic in omega. This is the background, it is all there. Okay. X naught is in omega, and then you always have all the balls which you are considering. Whenever you have a ball, this will be compactly embedded here. What are all the balls? So, we are working only at that point. Okay. So, these assumptions be all right. So, the estimate and alpha be a multi, let alpha be a multi index. Okay. That means alpha is equal to alpha 1 etcetera alpha n. then you can compute. This is the point wise estimate, that is what you have to see, that d power alpha of u, you see, estimate alpha the derivative where alpha, mod alpha equal to k, recall the multi-index notation, is less than or equal to. So, let me precisely write down an estimate 2 power n plus 1 nk whole power k by omega, omega n is the volume of the unit ball, r power n plus k into norm of u, the integral value which we call it L1. Okay. If you are not familiar with your notation, just see that it is just integral value. Okay. This means integral of modulus of u of x dx, okay, over the ball of radius x naught. So, you see the important thing in this estimate, left side is a getting point wise estimates is a difficult thing. This is a point wise estimate, you see, point wise estimate derivation is generally a difficult job, point wise estimate. LP, L2, L1 that estimates are slightly easier quite often. This is integral estimate. You see. Once you have this estimate, so I will not be proving all this. Once you have this estimate, you can prove analytic. This estimate will prove, though I will not think prove it, but that is it, will prove analyticity of u. You can show that the series converges to ux, analyticity of u. So, you see it is not just about the all differentiability of all orders, it is also important to have the correct estimates so that error terms converges properly, formula whatever it is, to make it a function u of x. So, this is a bit of analysis which you will be learning it. Okay. So, forming series is not enough, you have to understand what happens to the tail of the series. Okay. And this kind of good estimates, good derivatives will give you this one. So, let me tell you, so do not get worried about these complicated estimates, you try to write down this estimate for a simple case, and it is enough to prove there, then it is enough to prove when alpha is a special case 0 etc 0 1, this is the ith case, this is the ith vector, okay, ith case. So, the other thing will follows by induction, then you keep on applying, follows by induction. You can apply an induction argument to prove for any derivative. So, you prove it only for one. In this case your d power alpha of u is nothing but du by dxi, you see. So, it is enough to prove for this. Once you prove it all for first order thing, you can repeat it, because you will be able to, because if this is there, you can repeatedly apply for du by dxi to get the other derivatives. You can, and you can explain the fact, you can get back the factor correctly. That is true when alpha is equal to this one, your mod alpha is equal to 1. So, in that case your k equal to 1, you see. When your k is equal to 1, you will get everything. So, you see 2 power n plus n, k equal to 1, and this is 1, and then exactly 2 by you will see what is the estimate you want to prove it. That is to prove, basically you have to prove this, to prove. So, which you will be able to do it, that is what it is enough to prove. You write down that estimate for the 1k when alpha equal to 1, it is enough to prove this is equal to less than or equal to I am rewriting that estimate in this special case, n plus 1 n by omega n is the estimate you want, norm of u power L1 of Br of x naught, you see. Okay. So, this is what you want to prove. Again the remaining thing is induction. So, you see that one. So, as I said, what I will skip here is some argument. You have to apply mean value theorem. The proof is the application of mean value property and divergence theorems. So, you may have to apply mean value property basically. So, you see again the mean value property, using this first derive this one, first derive. So, this is an exercise, I will leave it, that you can leave it as a derive exercise. What I will prove is the first to derive this. This may be easy, du by dr at x naught du by dxi, sorry. So, first derive du by dxi, okay, the less than or equal to 2n by r norm u at L infinity of boundary. This you can write down the mean value property. This is by mean value property. You see this estimate, the difference between previous estimate and this estimate is different, you see. So, write down du by, you know, using the mean value theorem you will be able to write down the value at a point by the average for any ball, even for any ball inside. So, you have to apply this mean value property to the right ball. So, you have to apply this result for d r by 2 basically, you can do. So, you can apply mean value property to any point you like it. So, any point you can take the any ball you like it. So, you take a ball of radius r by 2 and then apply the mean value property, you get this estimate. So, that you can derive it. So, once you derive that, a little more work, I given it in the book, but it is better that you do it something independently, du by dxi. With that you can derive whatever estimate we want it. Okay. Yeah, no, with that you can you have to do one more estimate before proceeding work. You prove you can get an estimate on u, your u of x, okay, less than or equal to 1 over omega n. I am skipping few steps. So, you may feel that how it is done, but you have to do it. N norm of u L1 of Br of x naught. Using this, these two, you can also do this one, combine, we get the required estimate. Into 4 du by dxi and at x naught, and that by induction will give estimate for d power u of at x naught, and that by some argument will give analyticity. So, these are the various steps. So, let me derive an interesting result which you know in complex analysis, what we call it a Lioville's theorem. So, if you look at it, complex analysis, those who are familiar, you know that the real and imaginary parts of an analytic complex analytic function satisfies mean value property. There also you prove this mean value property. So, the basically all this is part of your harmonicity. Okay. Suppose u is a bounded, this is what a bounded harmonic function in Rn. Boundedness is important, right? You know that, just like a bounded anal function is basically the harmonic function property. Then u is a constant. U is a constant. This proof is now from the previous estimate. In the proof, from the earlier proof, we have du by dxi, modulus of du by dxi is less than or equal to constant into c by r into, now u is given to be a harmonic in Rn. So, you can take any ball you like it, in particular you can take Rn and you get L infinity. Okay. So, you have this. This you could write because u is given to be harmonic and bounded in here, and this is a bounded quantity. This is a bounded quantity, bounded. So, this is less than or equal to some another constant by r, and this is true for all r tends to infinity, for all r tends to infinity. So, that implies, so this implies immediately du by dxi is equal to 0. That implies u is constant. You see. So, the first estimate in the beginning estimate will give you. So, you do not need the entire thing, you need only the first derivative estimate, that is the first estimate which you get. The one thing is, two things you are applied, u is harmonic. So, you get L infinity of Rn, and that is a bounded quantity. The L infinity is the supremum, okay, essential supremum we call it. So, let me not get into that one. For continuous functions it is the supremum, normal, maximum or whatever it is, and that is finite, that is given to be because it is a bounded function. So, you have your harmonic functions. Okay. So, what do I want to? I want to state before completing today's lecture, and then we will go to another new topic, what we call it an important result, what we call it a Harnack's inequality. So, I am deriving many things. Again I am, as I said, all the proofs I will not be able to give it, but then I am giving you some complete proof, some idea, that is what we do it in course, right, and some we skip completely. So, what is Harnack's inequality? Let V compactly contained in omega. So, you have a domain omega and you have a V, whatever be the domain, V be a domain in omega, be a region and u greater than or equal to 0 be harmonic in omega. This is a kind of again a very point wise something comparison between the values of two different points, that is a very crucial thing. So, you are comparing the values. So, earlier you are estimated the value, now you are comparing the values omega, then there exists a constant. See, that constant will depend only on the dimension n and V, nothing else, such that, so it is a kind of a universal constant, okay, V, such that supremum of u, you see, estimating V is less than or equal to infimum of u. Yeah, that is a very interesting, and this is true for any harmonic function. This is a very So, you just see that since the supremum, that means this gives you your u of x is less than or equal to u of y for all x and y in V, right. You take any x and y, you will see that u of x is less than or equal to u of y, some constant, of course you have to see that constant. So, you see you can estimate that way. This is the famous Harnack's inequality. So, let me not try to give the entire proof, you should go and read the entire proof. So, in this case, so let me go to the in particular, that is what I said, in particular, you see I already mentioned, so let me write it. Okay. In particular 1 over c u of y less than or equal to u of x less than or equal to c into u of y. This is true for all x, y in V. So, it is a comparison, you are comparing the point, and there is a somewhat a given V and the dimension of the problem, you have a universal constant. Of course, from V to V change it, just I wrote omega here, this is not omega, this is your V. Okay. So, you have your domain. So, let me give you the idea of the proof, so that I can idea of the proof. Okay. Again mean value theorem property, you have to use mean value property cleverly. So, what you do is that for the mean value property, the whole idea is that you look for your domain omega and V is contained there. So, you take a V here. So, when V is compactly contained, it will have a distance. So, you call that distance to be d, the boundary, the distance between V and boundary of omega, okay. And this happen to be positive, because I am going to construct small balls. Then the next step, so you have a, so if I consider 2 points x and y in V, so if you start with any 2 points x and y V, and I want to find this constant, first I will prove an estimate, first I will prove a similar estimate when x and y are close enough. Okay. So, the main idea is like that, you prove this estimate when x and y are close enough, then try to cover your view, cover V with small balls whose distance is small. Okay. And since V bar is compact, you will get a finitely many things, and then you will be able to prove, you take the minimum, infimum and supremum, that is the basic idea. So, try to get this estimate when x and y are close enough, okay, with a uniform way, and this constant coming should not depend on anything else, it should depend on only V eventually of that distance, nothing else. Okay. So, that is what we are going to write here. So, you take x and y V such that x and y is less than r by 4. The reason I am taking this small ball, smaller ball, so if you consider x balls with center x or small center y, it will be within the domain. Okay. So, that is also the, okay, that is the whole idea behind that doing. So, can whenever you take a ball here, x here and y, so the distance between x and y should be less than r by 1. So, you should be able to construct balls around it to apply your mean value theorem. So, you can write basically your ux equal to, I can construct a ball of radius r by 2 here, you see, and you say of about r by 2 of my uz dz. Okay. Then I can do something, there are some steps to be done. With this you will be able to estimate this. So, I will change this ball centered at x, right now it is centered at x, but then I will be able to make an estimate, I will keep this here, I will be able to make an estimate because x and y are close enough, I can change the center to y, and then I can see that that will be smaller. So, you will be able to prove something, and end of it you will be able to prove this inequality. So, this is the exercise, I will leave it. So, you should play with it. That so, these are all basic analysis, now PD is coming here, okay, and only mean value theorem, because x and y are thing you are integrating into a ball of radius r by 2, right. So, if you have x, you are considering a ball of radius r by 2. So, if this is x and this is y, I will be able to construct another ball here, okay, and that will have small. So, I will be able, so you are integrating over a slightly bigger ball, but then with centered x, which I can change to a ball with centered y, but with a smaller ball, and by this will x and y are close enough, I will be able to do this one, and then you just calculate the value, you will do this one. Now, x and y are symmetric, right, x and y, you can interchange x and y. You can get the other way inequality interchange, because x and y separate does not apply, instead of x you start with y, I can do the same thing, then I will get an x here. So, what I will eventually prove is that 2 power n u of y is greater than or equal to 2 power n u of x greater than or equal to 1 by 2 power n u of y. So, I got this inequality with a constant 2 power n, that depends only on n, not even on v, right. Now, what I do is that, so next step is what again I do this is one exercise, you can work it out. How do I change the ball from centered x to a smaller ball of centered y? To get this, you want to have a ball around y, okay. So, that is what you have to do it to get this, but that ball should be smaller, so that you can estimate from below, and then just interchange x and y, you get this estimate, okay. So, for a x and y are small enough, you get this one. So, now what you do is that you can cover your v by finitely many balls, finitely many v bar, rather cover v bar by finitely many balls, okay, open sets, and then each time you can estimate from x to y. That is a very nice way of doing that. You can I almost given the theorem, proves the theorem almost. So, two steps you have to think. First, you do it for x and y are small enough, which I have almost given. Change this integral to an integral over with centered y, by if necessary do it with a ball, maybe you consider the ball of radius r by 4, you will get this, and then interchange you get it, that is a trivial thing. From here, so x and y are small enough, you can do that one. Now, if x and y are any arbitrary points in v, you can reach x from x to y with finitely many steps, that is what we basically tell. So, you can go one by one from x to y1 to y2 like that to reach any 2 points. So, this you can do it uniformly by using a compactness argument v bar. So, you prove this theorem. So, I think I will stop here. Now, what I want to really do is about what next class, or let me prepare for the next class, what I am going to the representation formula. So, the next class, next couple of lectures, not couple of lectures, a couple of hours, I will prove representation formula using, okay, Green's function. Okay. Green's function is some sense is similar to fundamental solution, but not exactly fundamental solution. It has a singularity of the fundamental solution, but it also take care of some boundary condition. Using this, we construct, so I am getting you prepared for the next classes, construct Green's function for the for upper half plane Rn plus and any ball of radius this thing. Okay. Once you have a Green's function, you prove the existence, some existence, not in very generality, existence for in these domains, existence special, not that also not full existence in Rn plus and Br of x. This representation formula is already familiar to you little bit. So, let me recall before I conclude. You have already seen that if f is C infinity, so these are all general remark for my next as I said thing. So, please go through. So, if you before you want to learn further, so you have to get prepared whatever we covered in this lecture. So, f is Cc2 of Rn, then you have seen that u is equal to phi star of f, that is in nothing but integral of Rn phi of x minus y f of x y dy solves minus Laplacian u equal to f. You see. Okay. But so you have a representation. So, whenever you use a solution, you prove the existence of solution. So, what this is that when n greater than or equal to 3, when n equal to 2, this result may not be true. So, that is a kind of again an exercise. So, let me leave it as an exercise for you. Let us see whether you will prove it. N greater than or equal to 3, the converse is also true for bounded solution. Converse is true for bounded solutions. Maybe I will explain to you, since the time is up. Let me stop here. For n greater than or equal to, the converse is true for bounded solution. What I am trying to show that if u is a bounded solution of this one, then u has this representation. Okay. So, I will stop here and we will continue next time, and we will finish, as I said, in another 4 lectures, that is 2 hours. This Green's representation and Poisson other formulas we derive for upper half plane and the balls of radius. Thank you.